Okay. Greetings, everyone. Hopefully all of you can hear me. So this is supplemental instruction for CS11. Yeah. So today we're going to go over some operator review. We're going to do some review of if and else's, while loops, and just loops in general. And then if we have time, we'll also program our own ATM. So what are the basic operators we got? So we know the ones that give us a value, that returns a value. We have our addition, subtraction, multiplication, division, and then the strange one, the modulus. Essentially, modulus is the remainder after you do integer division. So I'm sure that you remember in your elementary school how you would only go to the first place, and then you would stop and you'd say R1 or R2 or whatever. That's essentially what the modulus operator is doing for us. And you can always think of it as like a clock operation, that the analog clock is modulus 12. So what happens if it's 1 o'clock and I say, what time is it going to be 12 hours from now? So it would be 1 plus 12 modulus 12, and that would be 1. And we can see that. So let me just open. So yeah, so if we have something, it's 2 o'clock, and then we say in 24 hours, what time is it going to be? It's going to be 2 o'clock again. But then if we say in 23 hours, what time is it going to be? From 2 o'clock, it's going to be 1 o'clock. So it's essentially doing the integer division of this and then giving you the remainder, but that it's a wrapping function. So imagine that you only wanted something to deal with letters, right? You do the modulus. You would figure out what is the distance between A and Z, and if you forget, you can always just print out the operation, right? So we know Z is going to be greater than A, so 25, and we want to get the result of 26 because we need to have both of them. So then we could have the modulus of 26, and then we're off to the races, and then we add that to A. And that would allow us to stay within letters, and that's actually used in a lot of cryptography. Okay, so those operators always have things on both sides of them, and so they're called binary operators because their bi is 2. There are 2 things, and these operators always return some kind of value, like integer or float or double value. In the case of modulus, it's only going to give us an integer value. Then we have operators that also are binary operators that return booleans, things that are either true or false. But that the things on either side of them, they might be booleans, right? Is true equal to true, but for the most part, we're using it for comparing values. Is 5 equal to 5, or is 5 not equal to 5, and so on and so forth. And one of the tricks that you need to sort of remember is that for the greater than or equal to, think of it just exactly, like type it out exactly how you say it in English, greater than or equal to, and the same for less than or equal to, because if you flip those operators, you're going to get bad news bears. Then we have some more operators. These are a little bit different. These are working strictly with booleans. This not here, this exclamation mark, is called a unary operator. Uni is one. It only works on one thing, and that thing is going to be behind it. And what not does is it inverts something. So if I say not true, then it's false. If I say not false, then that's going to become true. The and or operators essentially are relying on having something that's a Boolean on one side and a Boolean on the other, and then it's going to become a Boolean. Imagine if you go to a party and somebody says, do you want a hamburger and a hot dog? And you get both of them, you're happy, so that it is true. But if they only give you one of those things or they give you nothing, then that whole expression is going to be false. With or is just only one thing has to be true in order for the whole thing to be true. Oh, there we go, pointer, I like that. So or only one thing has to be true for the whole thing to be true. If they're both true, then the whole expression is true. So if somebody asks you, do you want a hamburger or a hot dog, and they give you both, you're a pretty happy camper. But if they give you nothing, you're going to be pissed off. Okay, bonus operators. Impress your family and friends. These operators are not, except for the bottom two and in some of the cases, these operators are not needed to know. You don't need to know them in this class or even in the next class. But if you know them for CS 21 and 23, you'll be far better off than most of the other students. These are considered bitwise operators. They work similar to like the or and the and, but they work on multiple bits. So the and or, when we were working with them, grab the wrong thing. So with the and or, we have something that's like true and true. Oh, whoops. It's lowercase. Sorry about that. True and true. These are booleans, right? Or the things that resolve to booleans. So you could say like 5 equals 5, right? This whole piece here. Oh, I lost my pointer. This whole piece here is going to become true. So it's essentially a Boolean that the and sees. But what happens is with the bitwise operators is imagine 5 in binary is so like 5 in binary is different in so this is going to be in decimal, and then in binary it's going to be 0, 4, 0, 1. So this is the first place. This is the first. 0 2 to the 0th is 1. 2 to the first is 2, and 2 to the third is or 2 to the second. Sorry, is 4. So let me do that again. So each of these positions represents a power. So essentially, the first bit here, right here, is 2 to the 0th, and so it's a 1. So let's just write this out. You can see I don't trust a lot of calculators. Let's clear history. Okay, so and essentially all we're doing is we're just adding it up. So we have 4 bits. The first bit is going to be 2 to the 0th, and that's going to be, and then we're going to multiply it by whatever the value is, which it's either, this is going to be either either a 0 or a 1, right? And then this is going to be 2 to the first times whatever. It's going to be 2 to the second times whatever, and then this is going to be 2 to the third times whatever. And so essentially when we have zeros here, this is just a 0 here. When we have a 1 here, and there's a 1 here, it's a 1 here. And then we have a 0 here, so this is going to be 0, and then we have our 1 here. So essentially what we're doing is that we're choosing whether or not, and we can see the result is 5. We essentially choose whether or not we're going to add 2 to these individual powers up to be able to generate these numbers. So that's just binary. So now a bitwise essentially looks at those values and then does essentially the true-false operation on all of them. So let's explore. So let's do the bitwise of 3 and 2. So if I represent them, so we have 0, 0, 1, 1. This is 3. So this is in binary. This is in decimal. And then in binary of 2, it's 0, 0, 1, 0. Right? This is the 1s, this is the 2s, this is the 4s, this is the 8s. And so that's 2. Okay, so now what we're going to do is we're going to do the AND operation. Okay. So essentially what we do is we do the ANDs up, down. So false and false is false. False and false is false. True and true is true. And true and false is false. So this is in binary. And notice that we got our decimal of 2 when we did that. So now let's do 1 and 3. So in binary, 1 is going to be 0, 0, 0, 1. In binary, 3 is going to be 0, 0, 1, 1. And so now, oops, yeah, okay. So 1 and 3. So now we'd say in binary, false and false is false. False and false is false. False and true is also false. True and true is true. So the result in decimal is 1. So when we do the bitwise of 1 and 3, we get 1. Cool. So this is bitwise of AND. So now let's do the bitwise of OR with all of these. So we're going to change all these. Okay, so 3 or 2, the bitwise of 3 or 2. So binary, 0 or 0 is 0, so false or false is false. False or false is false. True or true is true, and true or false is also true. So we notice when we did the bitwise of 3 or 2 that we get the decimal of 3. Okay, so what do you think is going to happen here when we do the bitwise of 1 and 3? So 0, 0, 1, 1, which is decimal of 3. Cool stuff. So those are bitwise operations. They're not needed. You don't need to know them in this class, but they're very cool. XOR is also another bitwise operation. XOR is exclusive OR. So it means that only one thing can be true. If 2 things are true, then it is false. And it works exactly the same. I mean, same concept. I'm going to skip complement. So then these guys here, this is where I apologize profusely. So if you remember before, we're essentially limited to ASCII and the kind of symbols that we can use when we're programming in C++. And so as a side effect of that, we end up having to double dip and use the operators for multiple things. So remember when we do our C in and C out that we use these both of these operators. And the same thing's true with like the multiplication operator. It has other uses. It's been what's called overloaded, where the operator means different things, that we use it in different ways. And so, for the insertion to stream, that's where we do our C out, and then our extraction from stream, right? So insert into stream. So we have the stream, which is your screen, your terminal on your screen. And what you're doing is that when you use that operator, you're inserting into the stream that eventually goes to the screen. And then this operator here, where extraction from stream, we're extracting from the keyboard and then putting it into the value. So for this, we have our C out, and then on this side, it's whatever we're putting onto the screen. Versus here, we have our C in, this is the keyboard, and then we have wherever the variable is going. So imagine that it's actually, the data is going the direction of the arrows. So that's the use of these, the insertion and extraction stream. But there's also shift left and shift right. So back to binary. So let's work with the same numbers. Let's work with these guys here. So essentially, actually, we're just gonna keep going here. Essentially, what happens is that when you shift, you're moving everything over, and you're moving it over in this form here. So let's take 2. We're going to take 2. I'm going to shift it over once. And so essentially imagine that all of these bits we shift over once. So we go from 0010 to 0100. What happens is that what fills in on the back are zeros. And anything that falls over the edge on the front part is going to just vanish. So if you can only express 4 bits and you shifted this over 2 more times, so if you shifted it 3 times, you would end up getting a 0. So let's do it twice. So we're going to shift 2 over twice. So essentially we're going to take this and shift it once more. So it's 1, 0, 0, 0. And then if we take 2 and we shift it over 3 times, that's just going to be a ton of zeros because this 4 has fallen off the edge. If we could only express 4 bits. If we have more, like an integer has a lot more than 4 bits that it can store information. But shifting is really cool. And then it works, and so essentially when you do a shift 1, it's essentially the same as multiplying it by 2, right? Because we get the 2 and then we have 4. Here we shift it over twice. That's essentially doing 2 to the 2nd power. And so that's essentially multiplying it by 4. So we went from 2 to 8. Here, when we shifted it over 3 times, if we were allowed more bits, we would end up getting a 16. But if we only had 4 bits, then we would get 0 because we can only express things from 0 to 15 with 4 bits. Okay, cool. So that's shifting, and then the other way works exactly the same. It's essentially like dividing by powers of 2. Okay. So in class, we already reviewed conditionals, if and else's. This allows us to change the course in which our programs are running. that you only want certain things to happen under certain circumstances. So maybe you ask the user to guess a random number between two values. And if they don't give you the proper input, you probably want to like balk at them and say, hey, that's not proper input. And if they gave you proper input, you say, you know, thanks very much, and you continue with your program. And so the way that this is the syntax that we have in C++. And hopefully we split it up into multiple lines, and then we don't have it just all in one line. And so essentially, you have your condition for whether or not you're going to run it, and that's going to be true or false. So actually, I should have, there we go. This is from a previous supplemental instruction. And so we have our condition. So let's just say, let's make a variable called t, and we're going to assign it to 31. And so then what we do is we're going to compare t to 50. If t is bigger than 50, we're going to print out yo. One of the cool things about if-elses is that there's also else-ifs. So just the normal if-else is essentially one thing or the other is going to happen. So either this is going to happen or this is going to happen, and that's it. But what you could do is you can chain them. You can say, well, if it's greater than 50, then do this. But if it's greater than 20, then do this. And so, what's the conditions here that this will run? Right? If I type in 60, this will never print out, because what happens is that this if happens, and then we're done. So this is actually going to be the same as if I said and t is less than or equal to 50, right? But I don't need to put any of this because I know that this t here is going to handle that for me. I mean that this if here is going to handle that for me. But it's essentially the same. That it's a filter. You can think that the things on top hopefully are going to catch most of the cases, and then as you sort of percolate down, that they're going to be handling less and less cases. So here, right, we're only going to be handling things that are equal to 50, between 50 and 20, not including 20. We'll print out dog, and then if the value is anything besides that, we're going to print out smalls. Right. So this is the same as if we said, well, as long as t is, and actually I should probably say that I made a mistake there. Oh, no, that's right. Same as t is greater than, oh, yeah, I have an error here. So this would be the same here as if I said else if t is smaller than or equal to 20, that we would print out smalls. And so we don't necessarily need to actually write that. We don't need to write else if, because we know this else is just going to cover that case because it's anything besides that. So what's going to happen is only one thing is going to print out in this whole block, no matter what value t is. Right? If t is 5, then what is going to print out? Smalls is going to print out. Right? If t is 5,000, what's going to print out? Yo is going to print out. Because yo prints and then we're done. We don't keep going. But then, if we notice this lower part, other things print out as well. So now, and this is independent of this in the sense of what's going to print out. So when this is separate from the above ladder. So now we say, and now we're going to make a Boolean called isBig, right? And it's defaulted to true, but now we're going to assign it to whatever the Boolean is of this. if t is greater than 30. So t is 31, and so what is this whole expression going to become? Is 31 greater than 30? Yes, so it's going to become true. So is big is going to be true. So now we say if true, as big is true, we print out is big yeah. So if the user types in 31, or the variable just is assigned to 31, what's going to print out? Dog is big yeah. So now what if I said 20? What's going to print out now? So is 20 greater than 50? No. Is 20 greater than 20? No. So we print out smalls. And then is 20 greater than 30? No. So is big is false. So if false, so we don't print this out. So all we print out is smalls. Cool stuff? And so you see how, in this case, we just print out different things based on the values that we have for t. But imagine that maybe you had menus that the user was going through and pressing buttons, and that you were then asking them to do different things based off of that. So maybe you ask them an initial question, and then you have this if-else ladder to figure out how do they answer, and then for each of the answers you have additional questions for them. So that's what if-else is for. Okay, so loops. So in C++, we have 3 primary loops that we use. There are other structures, but we're really going to only use these 3 loops: a while loop, a do-while loop, and a for loop. And they can all sort of be used interchangeably for each other, but I would highly not recommend them because they're all specialized for specific things. A while loop is really good for running, both a while loop and a do-while loop are really good for running an unknown number of times. That maybe you're depending on user input or waiting until a game is over until you exit the loop. A while loop, essentially, you don't know, a while loop might never run based on the condition of the while loop, as opposed to a do-while loop, where a do-while loop is guaranteed to always run once. So a do-while loop is really useful for a game where you're asking the user to make a move, that you know that the user is always going to make a move, and then based on their move or the result of their move, you decide, there's a condition in the while loop to decide whether or not you're going to run again. A for loop is really good for counting things or going a certain number of times. The moment you arrive at the for loop, maybe you've collected all the variables and you know exactly how many times you're going to run for. That's what a for loop is really good at. So counting things. Or going through, going through each letter in a word or something like that. You're not skipping anything and you're not just randomly stopping. Yeah, so while loops may not necessarily run at all based on the condition. A do-while loop will always run at least once and then look at the condition. And a for loop is really good. A for loop is really good for looking for knowing exactly how many times you're going to run beforehand. So let's see if I can find my loops. Okay, yeah. So this was from a previous SI session this semester. So here's some examples. So here's a while loop. So while t is less than, so this is me using a while loop, how you should use a for loop. Because essentially all a for loop is it's a while loop in a particular format. So actually let's start with a for loop. Why not? So the syntax is a little bit weird. So we have our int I, and we assign it to 0. Essentially, I is going to be our iterator, or the thing that's going to be holding the count that we're going to be counting to. And then we have a condition for whether or not we run or not. And this condition is gonna happen at the beginning of each loop. And if it's true, the loop is going to run, and if it's false, the loop is done, and then you arrive at the bottom. This is a little bit funky. What essentially happens here is this runs at the end of each loop, iteration of the loop. So this piece here happens once at the beginning of when you start the for loop, and then it doesn't happen anymore. It only happens once. This middle part happens right before each time the loop runs, and this happens at the end of each loop. So we start out with I. Oh, let me get rid of that. We start out with I being 0, and so then the first thing we do is we check whether or not 0 is less than 5, and it is. That's true. So now we print out for 0. Then we start and then we hit the bottom of the loop and we run this. Go I++, which makes I 1. So now we say, is 1 smaller than 5? It is. So we run this loop. We say for 1, and then we do it again. At the bottom of the loop, we increment I. So now it's 2. We print it out for 2, for 3, for 4. And now after for 4, we go here, we hit this guy, and then we increment it. So now it's 5. Is 5 less than 5? No, it's false. So then we drop out, and then we return. We're done. The program's done. So this is really cool for us. We know that this loop is going to run exactly 5 times, from 0 to 4, from just looking at it. But sometimes the while loops or the do while loops, you don't necessarily know how many times they're going to run. In this case, we do, because we can look at it and it's not relying on user input. This is essentially doing the same thing that a for loop would do. But imagine that instead of t equals 0, that this was user input. Maybe we did like a cn to t, right? Now we don't have any idea how many times it's going to run, right? And we would actually get rid of this, right? The loop would continue running. Oh, and then we would have to take this loop would run forever if the user entered in something that was less than 5. So now we would say cn t, right? So now each time the loop runs, we're going to ask the user for some input, and right now we're being rude. So maybe we would say cout, enter a number less than 5. Right. It's rude to not tell the user that you're expecting them to type stuff. So here, this loop, they get stuck forever if they comply with your request. So maybe that is not less than 5, or maybe that's if you want them to be able to escape and you want to give them good advice, okay, you're going to change that prompt appropriately, and then you do the same thing up here, right? Because we're taking input up here. So whatever. So here we don't know this while loop. We have no idea how many times it's going to run, because it's all dependent on what the user types in. And notice how we sort of have 2 lines that are exactly the same in this while loop. I mean, outside of and inside of the while loop. And so this is one of the problems about using a while loop, when you should really be using a do while loop. Because in the do while loop, right here, makes a lot more sense. That this right here, you only have the 2 lines. You don't have 4 lines. Because you always run the loop once. And then at the end of the loop, then you check the condition. as opposed to up here where we either had to take in user input beforehand, or you needed to set t to something so this would be true, so you would run the loop at least once. So do while loop is much better for when you're taking user input and you know that you want to run at least once, as opposed to a while loop where maybe you never want to run the loop because of what a user entered in. Right. Cool. So while loops are good if you don't necessarily want to run ever, and if you don't know how many times you're going to run. A do while loop is really good if you want to guarantee to at least run once, and subsequent is based on some kind of other variable. And then a for loop is really good for when you know exactly how many times you're going to run. And so this 5 could be some kind of variable that you maybe ask the user, what is your age? And then you have your variable called age, right? Cn age, int age. And so then instead we say cout, are we there yet? Right? The older you get, the more times you ask, are we there yet? So I'm sure this is very applicable to being on a road trip. While we're looking at the code right now, you know, in the source code, we don't know how many times this is going to run, but we know from the one user input exactly how many times it's going to run, and that it's going to be a set amount based on this age. And so my advice is the moment you hit this line in a for loop, that you know how many times the for loop is going to run, as opposed to in the while loop where nowhere do you know in the code until you're done, essentially, you know, until the CN actually meets this condition, do you know how many times your loop is going to run. So for loops are really good for, you know, at this exact moment you know how many times you're going to run. Cool. So we have our while loop, our do while loop, and our for loop. So now we should actually have pretty much all we need to be able to write our own ATM machine. And what we're going to be coding is going to be pretty similar to what real ATM, what the code looks like on a real ATM. It might be a little bit more complex, but not much. I mean, the logic, you're essentially going to be able to write all of the logic. And so I guess the first question is, and we're just going to say that this ATM only works for one person. So we're just going to have one balance integer for that one person. Maybe the card was already read. Like somebody else wrote all the code to read the card, and then it made an integer called balance, and then we're going to be using that. And so now we want to imagine that the user needs to be able to do multiple of these things, right? Maybe they want to withdraw some money, and they also want to look at what their balance is after they withdraw it. Or maybe they look at their balance first, and then they know how much money they need to withdraw. And then after they're done, they're going to exit. That you want to have them actively make those decisions. So that means that we need some kind of loop structure. And we don't necessarily know how many times we're going to run the loop. But we know that the person entered in their card, so we're guaranteed that there will at least be one loop. And so this is a really good situation for us using a do while loop, because we know that even if they don't want to do anything, if they just wanted to see if it could read their card, that they're going to exit. And that would be the condition for us getting out of the loop. So maybe you have some kind of Boolean that's going to be keeping track of whether or not the person pressed the exit button or not. And then, and to know whether or not they press the exit button, right? We're gonna take in our input, and then have some kind of if-else ladder to figure out what operation they asked for. And if they withdraw, then you're gonna reduce the balance. If they deposit some money, you're gonna increase the balance. If they're just going to, if they ask to display the balance, you're going to print out the balance and such. So yeah, so I'm going to leave it up to you to write this out. Feel free to email me if you want, if you have any questions about this, or if you've done it and you want me to look it over. I'm happy to do that. So so I'll give you my email again. So it's cs11@carterfrost.com. When you send it, I have multiple email addresses, but if you send it to that particular email address, it will be marked with a flag, saying like, "Hey, this is really important. This is actually a real student," as opposed to just one of my other emails. Cool. Okay. So let's do a little bit of a review. So we talked about operators. That we have our binary operators, things that need things on both sides, and they either return like a value or a boolean, which is also value. And then we have our unary operator, like the not, that only has one thing and it inverts whatever it is. And then we have and then we had all of the other fancy operators to impress your family and friends. And then we did the if-else review. So this allows, the if-else allows us to take different paths in our programming to do different things based on certain conditions being met or not being met. Then we have our while loops. And we have our do while loops, and we have our for loops. This allows our programs to do things over and over again, or not to. And so while loops are good for running not at all, or running a number of times. A do while loop is really good for running guaranteed always once, and then subsequent times will be based on the condition. And then for loops are really good for counting. Then I talked a little bit about how you might program an ATM, and I'm going to leave it up to you to do. And feel free to email me. It's not required at all for the class, but it's just a fun exercise to do. Cool. I'm going to see if I can sneak in another presentation into the time today. So let's see. Okay. Hey everyone. Welcome back. So I'm going to talk a little bit about some of the more advanced topics that hopefully we'll go into next Wednesday in actual class, but I thought I might as well expose you all to it here. And so just going to review if else is really quick. We're going to talk about scope. We're going to talk about flowcharts. We're going to talk about C strings versus C++ strings. We're going to talk about comparing strings, precision, and then substring. So if else or conditionals are used to take different paths in a program. And so in this case, either this is going to happen or this is going to happen. But you can have multiple else ifs in between them so we could make different decisions. So scope. When somebody says something's out of scope, that means that maybe you did something inside of some curly braces that you were expecting that you would be able to use them outside. And so essentially what happens is that any variables that you make inside of any set of curly braces won't be accessible outside of them. So whenever we're in an if or a while loop, or even in main, anything that we create is going to be local to that whatever that set of curly braces is. So let me just make an example. So I'm just going to CP blank to scope. Okay. So essentially, anytime if we make a variable inside of main, and then we had something that was outside of main, we're not going to be able to access it. But a better example is maybe I say if 5 is equal to 5, right? Something that we know is always going to happen. Okay. You should always comment your bottom curlies. Very important, because when you get lots of them, you can't tell what's going to happen. So here we can say int t equals 10. Now, if we were down here and we said cout t, we're going to get a compiler error because t doesn't exist. So let's do that. Just so we can see the error. See, t was not declared in this scope. So when you see that error, you know that your t is out of scope, in the sense that that t was created inside of a set of curly braces and doesn't exist outside. So right here, we could just say like int t equals 50, right? So now we have two t's in main, but this t here is only accessible inside of these curly braces. The moment we hit this bottom curly brace, this t vanishes, and then this t comes into existence. So now we can compile it, and we can run it, and there we go. We got our 50 greetings. So let's say that I actually did want that value for t that happens in this if. What I do is that the things that are happening inside of here, inside of this if, it inherits everything that's outside of it. So if t existed outside, I could say int t equals 0, and then here I could just say t equals 10. I can get rid of this. So now what happens is the scope of this t is in main. Everything inside of main has access to this t. And so this if, the scope of this if is inside of main, it's inside of main, and so it has access to everything that main has access to. But anything that the if block has access to doesn't necessarily, main doesn't necessarily have the access to it. So anything that we declare, any variables or whatnot that we make inside of this if aren't going to exist outside of this if. But anything that we make outside of it in main, this if is going to have access to. And so this, anytime you have a set of curly braces, essentially imagine it that you're in a block, whether or not it's in a loop or whatnot, and anything that we create inside of it is going to vanish afterwards. But anything that was created outside of it, and then maybe we changed inside of it, is going to stick around. So in this example, we made t outside of it, but we changed t inside of it, and we see that t has changed outside of it. Cool? So that's scope. So anything that is inside of a set of curly boys or curly braces is going to be inside of a block. And you can just randomly make your own block. If you really want to, you don't necessarily have to have it in an if. You can just have a random block. Maybe I want to make a ton of variables, int s. Maybe I want to just make a ton of variables inside of a block, and that I don't care. And that I don't care about having access to them outside. I would not recommend doing this. Just know that you can. That the language allows you to do, just to make a random block. Really, the block should belong to something that is actually doing something. So an if or a while or a for loop or something. Yeah. I'm not going to say that. Okay. So now flowcharts. Let's talk about some flowcharts. So right now we've been dealing with pretty simple programs, but as the course progresses, you're really going to need to write things down on paper and plan out what you intend to be doing with your program before you even start writing any code. And so one of my recommendations to doing that is making some kind of rudimentary flowchart. And so I'm just giving you four different symbols and then an arrow to connect them to be able to sort of break down a program. There's a lot more of these symbols in just generic flowcharts, like how you'd organize an organization. And no matter if you're doing any kind of programming or any kind of complex operations, flowcharts are really useful for being able to communicate to other people a process for something. For example, I have made flowcharts for the operations of setting up a security device. And I was able to then give that flowchart to somebody else who they then spent the next month writing all of the code and implementing that. So I didn't need to know how to code any of that. I just needed to know how to express to the person the process that I wanted the code to take a person through. And so, for me, it only took like a few hours to make the flowchart, but for them, it took them a month to program. And so I was able to delegate my work. I was able to give my work to somebody else. And then I was also able to make flowcharts so that when I moved on to other jobs, that people could do the work, that people could go through and test things because I had made flowcharts. So it's really useful for coding, for being able to delegate off tasks to somebody else, but also really useful for being able to repeat something and to be able to do something the same thing over and over again, consistently. And so let's talk about the four symbols. So the first symbol here is called a terminator. It either begins or it ends a process. Some processes don't have an end. Others do. So for example, the ATM example, the actual exit loop, right? We had like an exit condition when we would arrive at the terminator, but the overall loop for a real ATM never ends, right? It's going to continuously run. Maybe it ends when it's put into some kind of diagnostics mode, but the general use of something in general, like an appliance, it's always going to be running, right? Your microwave at home, you'll be pretty pissed off if it only worked 500 times. And so the flow of the microwave is going to be continuous. There's going to be a start terminator when you plug it in, but there's not going to be an end terminator. Then we have the process box. This is essentially you doing some kind of operations, or maybe you're doing math, maybe you're creating stuff or whatnot. And then we have our decision diamond, or sometimes a decision triangle. This is essentially like where you would have like an if or else kind of statement, where you're going to be changing the course of your program based on some data that you have. And then we have our input-output box. So essentially, a lot of the times you're going to see some kind of input box right before decision, before you hit a decision diamond, a lot. If you're taking, like, in the code that you're going to be writing. Here we don't really have a good example of that here. But yeah, as a joke, so we start off, we say, do we have any homework? No. Let's do some computer stuff, and then we continue this loop forever until finally we actually do have homework. And then can we procrastinate? Yeah, we can procrastinate. So now we're in this big loop here. And then finally, when we can't procrastinate anymore, we do the process of doing our homework, and then we have our output of us turning in the homework, and then we start all over again. And then we're back in this loop, and then this loop, and then finally we do that, and then we're good. So a good exercise that I encourage you to pause the recording right now and do is maybe write the procedure for how you would make a peanut butter and jelly sandwich, right? It's not just one process, right? There's multiple steps that you have to go fetch the bread. You have to make sure you have jam. You get your spreader. You got to open the container. You got to pulp the bread. Maybe toast the bread if you toast it. Spread it on one side, spread it on the other side. You have these distinctive steps that you have to take. While that might be silly for a human to take, imagine that you're programming this for a robot. That everything has to be very literal. Oops. That everything has to be very literal. And literal means written exactly as it is meant to be expressed. I did an exercise in junior high where we had the instructor who was essentially pretending to be a robot, and we said, "Oh, well, put the peanut butter on the bread." And she just picked up the jar of peanut butter and just slammed it on the loaf of bread still in its plastic. Right? That's not good enough. You've got to be a lot more precise. You've got to take out the bread. You've got to open the container or whatnot. Maybe make a flowchart for your morning routine. Hopefully you have a morning routine. You have certain processes that you do. Unplug your phone, check your email, things like that you do in a particular order. So maybe make a flowchart to do that. And if you're really feeling like torturing yourself, maybe do a flowchart on how you do long division. Because there's steps, right? And at some point you're complete. Cool. Yeah. So stop the recording right now. Try to make one of those flowcharts, and then I'll see you in a few minutes. Great. Welcome back. All right. So hopefully you made one of the flowcharts. It's awesome and elaborate. You can show it to me later. Okay. So a C string versus a C++ string. A C-style string is essentially a bunch of characters. They're all slammed together. And so what happens is that at the end of all of those characters, they have a special character that is called a null terminator, and you can see that in the ASCII table. And that essentially says, hey, this is the last character. Stop proceeding from here. And then the other C++ style string is called is a class. So while that class may contain a ton of characters, like a ton of characters that are also attached together, the class allows us to do other things. Like the string is in a class of things. So it has lots of features that are accessible to us, as opposed to the C-style string, where there's no features besides that they are just that we can treat them as all individual characters. A class, there's things that we can ask of the string, and we'll learn about those later. For example, we can compare two strings. And with the C-style strings, we had to go, if we wanted to compare two strings, we had to literally write a for loop that would go to each position of them and make sure that they are exactly the same. As opposed to a C++ style string, which let's look at the documentation. So the documentation essentially says that if we say string1 dot compare string 2, if we get a 0, let me zoom in a little bit. If we get a 0, then they're equal. They're the same string. If it's less than, then the first character, or the character that's in the front, it doesn't necessarily have to be the first character, would be doesn't match. So you could have, Cat and Carter. The first character is going to match, but and the second character is going to also match, but the third character is not going to match. We have an R and we have a T that we're comparing, and so we're going to get either a less than or greater than based on whatever character doesn't match in the string. And so it's just going to keep going through the string and comparing each letter until it finds a letter that doesn't match. And if all of them match, then we get a 0. So right here, we can essentially write an if statement that says, let's compare them. If they're not 0, then we know that they're not the same. And so string 1 is not string 2. But if they were, right, if you said equals equals 0, then we could say is. We would just get rid of this not. What we can also do is we can give in all kinds of arguments, where we can chop up, where we can make a string. And I would encourage you to look at the documentation. Right? We have another string object. We have the position of the first character. We have the length of the compared. So notice how here we only had two things. We had string 1 and string 2. But then here we have lots of other arguments. We have this 6 and this 5. And so the way that you figure out what do these even mean is you look at the documentation and you look at this and it says, oh, well, there's the other, this is the str1. So str1 is this thing. And then what is this 6? Well, this 6 is the position of the first character compared in the string. And then the 5 is this length, the length of the compared string. NPOS, I'll talk about NPOS a little bit later. And then the actual string that we're comparing. So this is a string literal for Apple. So we're looking at, so we're essentially saying, hey, we're going to look at str1, where we're going to start here, right? That's the 6. Where are we starting? And then 5 is how far we're going. So we're essentially getting this piece here, right, of the string 1. So we start at 6, we go 5 in, and we're comparing it to the string literal of apple. If it's 0, then we know an apple is an apple, or a green apple is an apple. Right? Cool. Yeah. So whenever you're not familiar on how to use it, the documentation is pretty good on this website. It's not official. This is all on C++.com. This is not official documentation, but it's pretty much as good as we're going to get when we're working with C++. There languages like Python and Java have actual official documentation that the language, that the people who are maintaining the language release. This is essentially just maintained by companies and the community. But it's pretty good. I've found it to be pretty reliable. Okay, so now let's talk about NPOS. NPOS is part of the string class, and it essentially is no position. So if we wanted to say, if I asked you where in the string is this letter, or maybe this substring, like part of the string, and you wanted to tell me that it does not exist within the string, you would give me one of these NPOSes. So that's what NPOS is. Find is a good example of that. Let's see if we can find the find. For numerical value. String class. Here we go. Find. Here we are. So this find is going to give us the position of whatever we're looking for. So for example, there are 2 needles in this haystack with needles. And so we're going to look for needle. And so the way that we do that is we say str, so that's this guy, dot find str2. So we're finding needle in the haystack. This here is going to give us the first match. So it's going to give us the position of this guy here. If we wanted to get the last one, we would go back and we would look at the documentation. See, there's R find, the last occurrence. But let's say that it didn't exist. Let's say that there wasn't a needle in this haystack. We would get this string NPOS thing. And so this is the code for that we didn't find an NPOS, which means that we found it. And it's safe for us to look at found. Because otherwise found isn't necessarily safe to look at. Because if we found it, it's a nice number. But if it's not, it's this weird string object. So that's what NPOS is. Okay, cool. So that's so string comparison. We also talked about find and rfind. Now let's talk about precision. Oh boy. So maybe we're going to be doing assignment. We're probably going to be doing assignments that deal with money, or something like that, where we don't care about decimal places past 2 decimal places because it just doesn't make sense. If I say, hey, you owe me 0.5 cents, that's not, you owe me half a cent. That doesn't make any sense. And so we use something called precision when we're printing stuff out. And so we can do that 2 different ways. We can do it with this cout.precision. This essentially is just going to set the subsequent couts to it, to the precision of 2 decimal places. Versus this we would have in the middle of the stream. So let me show you. I thought I had a terminal open still. Here we go. Okay, so I'm just gonna use scope, the scope thing for this. So let's make a double, and we're gonna call it D, and it's gonna equal 5.55555. And then we're gonna say cout. We're gonna use this. I'm gonna say set precision 2 of D, and then we're gonna print a new line. And did I mess something up? Yes, gotta remember those semicolons. Okay, notice here it says set precision is not declared in the scope. That's because set precision, we need another class for that. We need the IO IMAP. And so let's go in and let's add that. It's another library that we need. That's the library that we need. Okay. And so now compiles beautifully. So let's run it. So notice it just rounded up. It rounded up to 6. So now let's change it to 3. What do we get now? And now we got right, this 10 is from something else. So let me just make this clear. Let me get rid of that. See, there we go. So we got three digits that we're showing. Cool. So substrings and find. So we already talked about find a little bit. So now let's talk about substrings. Substrings, we saw an example when we were looking at the compare and at find, how we could actually specify from where to where we wanted to look at it. So essentially what happens is that this is going to be in substring, this is going to be the position that we start at, and this is how many places we're going to go. But notice that substring also has this other set of parameters that we can give it, because it's overloaded. So let's take a look at the documentation. Pink. Okay. So here, this substr, where we start, where we end. So if we start off with, we think in generalities, but we live in details. We start at 3. So this is 1, 2, 3. So we start here, and then we go 5. So we got think. So this whole expression here is going to become the string think, which is going to be assigned to string 2. Then here we have our where we're going to find the position of live. So here, whatever this value, wherever this is, the integer value of this position right here, so that's going to be essentially like an integer at this spot. And so then we're calling substring at that number. And so what's going to happen is we're going to get all of this here, because this position here is where live begins. And when you only give one argument to substring, it's going to give us everything else left in the string. And so we can see that. Length is optional, but position is mandatory. And remember that in C++ and in most programming languages, we start counting at 0. So position 0 is going to be the beginning of the string. So don't make the mistake of typing in, putting a 1 here when you want at the beginning. It's going to be a 0 because we start counting at 0. Cool? Okay. Great. So we learned about strings. We learned about substrings. So we talked about if-else review. We talked about scope. Essentially, anything that is any variables that you make inside of curly braces are not going to exist outside of those curly braces. So if you want them to be accessible outside, you need to make them outside, but you can change them inside of the curly braces, and those changes will be maintained. We talked about how you can use flowcharts to draw out your programs, or to be able to just to write down a process in a way that's easy to communicate with other people, so that you can delegate, or so that you can repeat something very precisely that you've done before. I use flowcharts a lot for replicating certain behaviors for things. Like if I could get something to crash as part of work, as part of a testing procedure, I would make a flowchart in exactly how to make the thing crash, so that I could give that to a developer and say, look, I was able to crash it. Follow this procedure, and you can break that program too. And then we talked about C strings, how they're just a bunch of letters that are jammed together. And then at the end, there's the null character, which is an ASCII, versus C++ style string that has all these cool advanced features that has the find, has the substr, and whatnot, that make it very useful. We talked about how we compare strings, how 0 means that they're equal, and that the less than or greater than is just the essentially going to be the ASCII value of whichever letter is going to be greater as it iterates through it. We talked about precision, how you can get, if you want specific digits, that you can use precision, and there's the 2 different ways of using the precision. And then we talked about substrings, how we can chop up a string. Cool. So there we are. Blasted through that one session. So feel free to email me if you have any questions. And feel free to watch this lecture as many times as you want.